Hi, in the fifth lecture of this course, we shall look at induction and recursion. After looking at some of the foundational mathematics, including infinity, we are at the point where we can discuss how to define large sets and how to operate on its elements. That is what induction and recursion are concerned with. You probably have seen a recursive function before, such as these two, computing for each natural number, its factorial and its Fibonacci number, respectively. The key characteristic of a recursive function is that their definition contains a call to itself. This should raise suspicion because there's no denying that it does make the definition circular. In many cases, such as these two, that's not a problem. The function calls itself with a smaller argument value and eventually runs into a base case and terminates. But what happens when things become just slightly more complex? As in the case of this function, the so-called Ackermann function A. How do we know that it will terminate? As a matter of fact, this one doesn't. There's a bug in it. This is the correct Ackermann function. It terminates, and part of this lecture will be about concepts that allow us to show this and to rule out incorrect recursive definitions. In the first section, we'll start by looking at how recursive function definitions work and how large sets can be defined inductively. First, terminology. We shall use the terms induction and recursion nearly interchangeably, differentiating them mostly by what they are applied to. When defining sets, we speak mostly of inductive definitions, unless the sets happen to represent functions, in which case we also say that they are recursively defined. Later, we shall prove properties of elements in infinite sets, and those proofs are called inductive, and the technique is called induction. When we originally introduced sets, we hinted at ways of defining large, that is, infinite sets, but postponed its discussion. This is what we're filling in now. We already came across an inductive definition of a set when we discussed the transitive closure of a relation in the second lecture, and when discussing the closure of a set under a function. The general form of such an inductive definition of a set starts by defining an infinite number of sets like this. We start with S0 and a rule for how to compute from a set Sk the next set Sk plus 1. Note, Sk is always also part of Sk plus 1. So the sets never become smaller. Each step can only add new elements, never remove old ones. Eventually, the set S we want to define is the union over all these sets Sk. You can picture the process of computing S inside some set A by starting with some set X, which becomes our starting point S0. Then, step by step, we compute the Sk, and eventually combine all the Sk into a single resulting set S. Before we can apply this construction principle to the definition of functions, we first need to be a little more precise about the relationship between our usual way of defining functions and the view of functions as relations or sets of pairs. For simple functions, translating function syntax into the set definition is fairly straightforward. When a function is defined in several cases, we first look at the partial mapping each case defines. Note how the case condition becomes just an extra condition in the definition of that partial mapping. So in this case, for example, x greater or equal to 0. Each case defines a part of the function, and the complete function is simply the union of the part defined in each case. Of course, for this to result in a function, it is important that the cases not be overlapping and that they be exhaustive. That is, every argument value of the function occurs in precisely one partial mapping. So how would we apply this to recursive function definitions? Well, we could look at the partial mappings for each case and just build a union as before. However, in this case, this leads to a definition that is circular. That is, it uses the set about to be defined as part of the definition. Previously, when looking at the function syntax, we calmed our intuitive suspicions about the circularity of recursive definitions by reasoning about parameter values and base cases, but all we have here is a set definition that is blatantly circular. So we need to do better than that. So let's see what we can do with an inductive definition. Let's start with f0 being the empty set. We could put base cases in there, but not every recursive function definition has explicit base cases. So let's just start with the empty set. This is the step from fi to fi plus 1. We add the pair 0, 1, which happens to be the base case, as well as the pair n times fi of n minus 1 for each positive natural number n. And then we put all these fi together into one big union. The problem with this construction is that none of the fi are actually functions on the natural numbers, because they aren't defined for all natural numbers. So applying fi to any n in n and expecting a value back like we do here isn't going to work. So let's try again. This time, we keep in mind that all fi are not functions, but relations. They may be undefined for a given natural number n. f0 is still the empty set. But now, when we construct fi plus 1, we use fi to compute the image of n minus 1 under it. This will contain either one value, if fi is defined at that point, which we call v, or none, if fi isn't defined. As before, all the fi are then combined into a union. Note that in this case, nothing bad happens if the fi isn't defined at a given point. If it isn't defined for some n minus 1, then no pair will be added to the fi plus 1 for the corresponding n. And that's all that's happening. So this is now how we interpret recursive function definitions. For illustration, let's look how the fi are being computed in this case. In this little table, the first column contains the i's, the second the fi's, and the third is the recursive case of the next fi plus 1 that is derived from it. We start with f0 as the empty set like before. The recursive case has nothing to recur on, so it too is empty. For I equals 1, however, so F1 in this case, is the union of the empty set F0, the empty set computed for the recursive case, and the set representing the non-recursive case, the set containing the tuple 0, 1. With that, we can compute the next recursive case, and with that, the next Fi for I equals 2, and so on.